Looking at question number 5, we have two compounds, sodium hydroxide and potassium chromate. This is a setup for a double replacement, which means that sodium and potassium could potentially switch sides. If that's the case, then potassium is no longer going to be with chromate, but it's going to be with hydroxide. Now, I don't know if potassium hydroxide is going to be aqueous or solid, so I'm going to leave that as a little quick question mark. But since potassium is now with hydroxide, sodium can now be with chromate. And again, now that we've put those together and these are potentially new products, the question isn't just what's the new name of the product, but also is it aqueous or solid? And that's why we can use our solubility chart to figure that out. So potassium's right here, hydroxide's right here. If we look at the overlaps between them, that is an S. S, according to the chart, stands for aqueous. So that means that this is going to be aqueous. If we look at sodium chromate, here's sodium. Here's chromate, going down, going over. This ends up being an S as well. What does that mean? Remember, the S doesn't stand for solid, it stands for aqueous because it's S soluble. So in this case, after we mix them together, everything stays aqueous. So there's no solid that comes out of solution. So that means overall, we're going to say that there's no reaction, that this isn't a double replacement reaction that we would see any change happen to. So there's no reason to go any further. We're done with the problem because no reaction takes place. For our final question, number 6, you'll once again see that there are two compounds, both aqueous. Because they're both aqueous floating around in water, that gives the opportunity for the cations to swap places. If that's the case, ammonium is now going to move away from the sulfide. It's going to move to the bromide. So you've got ammonium bromide. We don't know if that's aqueous or not. And then zinc is going to move with the sulfide. So we get the new product, zinc sulfide. And again, we aren't sure if that's aqueous or not. But now that we have these two new compounds, we can check and take a look and see what it is on the solubility chart. First up then is going to be ammonium bromide. Looking at ammonium, here it is. Bromide's there. They overlap and intersect there with an S. S stands for soluble. So that means ammonium is going to be soluble or aqueous, AQ. Next up is zinc and sulfide. Then they overlap. They end up being an I. I stands for insoluble, which means solid. So this is going to be a reaction. Okay? So in order to be a reaction, let's start breaking these things down, right? This is like our AX. This is our BY. So let's start with doing some of our notes so that we can write this out as a full equation. So zinc is +2, bromide ion is -1, ammonium ion is NH4 with a 1+ charge, and sulfide is 2-. Ammonium, again, all this is on your chart, is +1. Bromide is a -1. And then zinc is always a +2, sulfide is a 2-. Now that we have all of those, we can just write our formulas out. For every 1 zinc, there's going to be 2 bromines, because zinc is +2 charged, and that is aqueous. Next up, you're going to need 2 of these ammoniums to cancel out with the sulfur, and that is aqueous. Next up, you're going to need 1 ammonium for every bromine, and that is aqueous. And last but not least, 1 zinc for every sulfur, and that is going to be solid because it's insoluble in water. Now that we have that, all we need to do is balance this up. Well, there's 2 ammoniums here, so if I put a 2 here, that's going to give me 2 ammoniums and 2 bromines. 2 bromines there, 1 zinc, 1 zinc, 1 sulfur. This balances out. 1, 1, 2, 1. And there you have it. That goes through all our examples of double replacement reactions. Continue to focus on what is it that I'm struggling with. Am I struggling with naming ionic compounds? Am I struggling with balancing? What is it that I struggle with? And then I want you to hyper focus on that. Get extra help with that so that you can tackle this problem. All right, good luck, science fam.